back. We are back. For those who know how to figure it out. And we are back. Let me make sure I shut my volume. And let's see if we see any more activity. So, no more music. The music is done. That's it for tonight for music. Let's see if we see any activity. Maybe that'll be a good thing for me to concentrate. And while I'm doing that, so the music is done. Let's see. Linda Moulton Howe. All right, I'm just checking my email. And Mom? And let me just go to my video manager to get rid of the one that was terminated. Terminated. Oh, boy. There it is. Let's get rid of that right now. I knew it was going to happen. Thankfully, we recorded that shooter. Thankfully, we recorded that shooter. So at least we're able to still see some activity. I think a lot of people probably said, go to bed. It's 3:23. Go to bed, Ma. We're seeing activity. All right, so it looks like the camera kind of moved off a bit. Or actually, Orion is moving upward and to the right, so I'm going to have to go outside and move that camera again. So we're done with music. I deleted the other stream. And everybody was messaging me about the Facebook turning blue. Cool. You guys rock. I'm just going to, like, nothing can happen now. I'm just going to go to YouTube and play my own music. For now, while I play with the camera. Okay, let's see. History. It's the easiest way. But at least we still managed to come back. Or maybe not so easy. Wow, I played a lot of music tonight. All right, let's do it. Let's see what happens. Nothing bad can happen now. I'll keep it low. I actually like my song. I'll be right back. All right, I'm back in. I moved the camera, and we won't do no music. We'll keep this one because this is prime time. At least we got that really great streaker before, that nice green tail shooter that looks like it exploded behind the tree. I will definitely upload that video probably tomorrow because that was really good. I thank you, Andy, for putting it on my Facebook, and Jello's got it on his channel, so you could definitely go check it out there. He put the link in YouTube chat. So at least it's somewhere because it's not on my channel. It's gone. It's gone. But there's Orion right there, center bottom of the screen. And that's where the activity is coming from, the Orionids. So we'll just keep an eye on that. And we saw a lot of activity. And like I said, this is it right before. What time is sunrise? I need to check that. I really don't want to not miss what I'm seeing on my screen. Okay. Let's see. Wow, 7:21. Oh my God, that's vampire time. 7:21. That's 4 hours away. Oh my God. Oh my God. I don't know about that. Holy. Hey, who knows? We'll not do any music. Maybe I should just do a radio show from the KGRA archives that I have access. Everybody has access, actually. It's free. Go to kgraradioarchives.com and you get any show. I just happen to have every show because I'm the producer. Okay, let's see. What's a good show in there? Let me go in there. I'll play what Mark from the other night when I got him to go on a surprise appearance Saturday night on Starborn. That was pretty cool. Bill was going off on the whole Tom DeLonge thing. All right, let's do that. This is a show I produced and went on Saturday night, and I brought Mark in.
RA Radio.
Oh, I've got to kill the other audio. Skywatch theme is still going on. Oh, I'm afraid to play any kind of music. I don't even know that theme music.
Designs and models.
Here we go.
This is what live radio's all.
People, scientists, researchers, and it seems he has made serious contacts with government and military officials in the pursuit of information.
All right, let's go to this conversation because it's all about Tom DeLonge. He brings it up.
There's going to be an awful lot of people there from.
And on his 6 hours, it summarized the best parts of all that footage. I had it hidden in my house for a period of time, and during that time, I was flying this person out along with somebody that was Werner von Braun's right-hand assistant. Werner von Braun, of course, as we know, this is Tom speaking, was a Nazi scientist that we brought over when the war ended to build our Apollo rockets. And on his deathbed, he told this person a bunch of stuff, and I was flying them out to Los Angeles, and we were taking certain meetings. At the time, a lot of weird stuff started happening. Yeah, pretty wild descriptions. I'm going to cut this down just a little bit because I thought I would have more time. But now, he also at times felt he knew too much and that he was being watched. He said in an interview, to give you an example, one time I remember bringing up a very specific craft that I believe we're building in secret to emulate the phenomenon that our government has been observing for decades. So I started talking about the craft, its magnetic slide system, and how it displaces over 89% of the mass of the ship, how it ionizes the engine, how it glows. I went through the whole thing. This engineer looks at me. This guy is about 70 years old, and he goes, "You better be real blanky blank careful about what you're talking about." And I go, "Okay, so I'm close." And he goes, "I'm not blankety blank kidding with you. You better really be careful." And he calls me up the next day and he goes, "I've had calls about you. If someone comes and asks you to get in their car, don't blankety blank get in the car." And he laughed and hung up. So I'm just going to skip over a couple of more things that he said. I read through the article. I've read about 5 or 6 different articles, and I'm going to give Tom the benefit of the doubt. He talks about an abduction experience he has had in the past. So now Tom DeLonge's big UFO announcement is come and gone. What was really good, what I think is a big announcement, is that he announced the creation of the To the Stars Academy of Arts and Science. he's created this company dedicated to the research of UFO phenomena from A to Z, and without being, as he says, suffocated by mainstream ideology and bureaucratic restraints. Now, that's kind of true. You know, that prevents a lot of research from happening. So can he do it? Well, he has partially shown us that he can by bringing together a large, diverse group of interesting and interested people, scientists, researchers, and it seems he has made serious contacts with government and military officials in the pursuit of information.
I wonder how he could have done that.
Well, I don't know. Money can do a lot of things, and you know, his time with Blink 182.
I mean, is he an engineer besides being a singer? Like, how did he? I'm just really curious. How? Well, I mean, he was with the CIA. He knew people in the CIA.
Yeah.
Like, I don't know. You know,
it's very interesting.
Yeah.
But you know, a lot of people were upset because there was no big reveal, no aliens, no craft.
It was just about going to the stars, but it wasn't like there's an alien contact and we have proof. I thought that's what everybody thought.
Well, you know something.
Now he's asking for money to support his thing, so I don't know.
I'm gonna take a different approach to this. I think that we have to be cautious when we have all these. I'm gonna just use this loosely. This term, these spooks from the government, and he's the outlet. And we have to be concerned about disinformation and what kind of information they're going to be dangling out there for him to put out there for the public.
Yeah.
You're talking about a guy from Lockheed Martin, Skunk Works for 39 years, project director, and some of these other individuals. And I'm a little bit cautious and concerned about what exactly they're going to be coming out with. Then you had Luis Elizondo, who supposedly worked within the agency that was detecting unidentified aerial threats. Now, he did say, we have clear, because I watched it, I actually streamed it. We have clear evidence, photographic, and I don't know if he said video, but I think he said photographic evidence, not this blurry stuff that you see. And I was waiting for something to be shown. And then I was looking on his list, there's no astronomer. You've got an individual like Mark Dantonio, and we've had him on in the past, and he mentions, he's got this project with detecting aerial phenomenon that's in the skies, this array that he's going to set up with Douglas Trumbull. To me, it makes sense if they're really serious about this.
Yeah,
bring a person like Mark Dantonio on board who's doing the on-the-field work. If you really want to make this global in nature and you want to incorporate all the possible avenues for research and development and just bring everybody in on this, I think it would be great to have someone like Mark involved. Because one thing we know about Mark Dantonio, he is one of the most grounded, factual, logical.
Oh, God, yeah. I agree.
Who better to analyze and at least put this out and in the public and say, well, you know what? Yes, this could be such and such, because that's what Mark does. And you know what? Sometimes they're afraid of getting the real answer.
Well, that's true. Yeah.
So maybe they don't want people to do real credible expert opinion on these so-called photos. So I'm a little apprehensive, but I think Tom DeLonge is really doing this genuine. He says he's been interested in this since he was a child in ufology. I think he's really doing this in earnest, and he really is being a person that is doing this for the right reasons. But I'm a little concerned about if they're taking him for a ride.
Didn't he say that all aliens are bad?
I don't think he said that.
He didn't say that?
No.
And actually, I don't know if you guys want to bring Mark in for 5 minutes, but he's willing to come on for 5 minutes. If you guys,
hey, let's bring him in, man.
Yeah, Mark is listening.
Don't let him wait outside.
Yeah, no, let's bring him in.
Mark.
Yeah, he's coming in right now. I'm adding him to the call. And this is what live radio is all about. So Mark will be joining us in a second. I'm trying to connect with him now. But yeah,
awesome.
I'm interested to see what Mark has to say as far as... So Mark, you're on with Julia and Michael.
Hey, Mark.
Julia and Mike, how you guys doing?
Oh, we're doing good. We're doing good now that you're here, right?
Oh, you're so nice. I enjoyed my time with you last time when I was on your show.
Yeah.
Thank you.
Very nice.
Thank
Enjoyed
you.
having you.
Yeah, we had a fun time.
So, what do you think of Tom DeLonge?
I have a couple of feelings about Tom. I actually wrote him the other day because I wanted to find out if he would be interested in backing our UFOTOG 2 project, which we've renamed to the Aerial Anomaly Detection System, AADS or ADS. And we renamed it because when people hear the word UFO, they run the other way. So I talked to Doug about this actually the other day, and I mentioned, hey, if we're going to look for funding for this, I think it's best if we rename it, rebrand it, and widen the scope of the project. In other words, make it something that can look for asteroids, make it, the killer asteroid, make it something that can look for meteors, and put these tracking platters all over the world. So it'll be the Aerial Anomaly Detection System. If you take UFO out of it, then science can embrace it.
Right.
And I think that's a better approach. And I got him to agree with me very quickly on that. He saw it and says, "Oh, okay." I mean, that's the extent of the argument it was. And I was like, "Yeah, okay." So it was good.
Yeah, that's really something else. I think it's a good thing. I really do.
Yeah, no, I do want to. You asked me a question which I actually didn't answer. I didn't mean to, but I kind of skirted around the question. I actually wrote DeLonge to let him know that we're doing this aerial anomaly detection system, and if it's something that he's interested in adding to his agenda, Doug and I would consider doing that. Because it's not like we're not elitists in any way. We think that this is a group project. Everyone should be involved if they could be. The data belongs to everyone, not just us. It's not how it works. So I think it's important to widen the scope a bit and to include everybody that wants to be part of it. And I suggested that if he wants to, we would certainly entertain that, because it's truly a scientific endeavor to determine whether they're here, and it's something that is small and can be deployed worldwide. Given the funding to create these new platters, and right. And we might be able to get funding from multiple sources, not like Kickstarters, perhaps, but maybe from in Canada, maybe we can get a Canadian firm to put up the money. In Africa, maybe we can get a national, an international relief effort to fund it, because it can look for things that are pertinent to to that. It doesn't have to look just for unidentified flying objects. It can also look for other things going in the atmosphere. It could track contrails, for instance, to get a good idea beyond satellites about the global spread of contrails on the planet, and then see them over time. I mean, there's so much that this can do. In other words, it's a listening post. It's a viewing post. It's something that can view the world. Right? Am I wrong? Tell me about that. I mean,
no.
I think that would be a great idea.
Yeah, absolutely.
To combine.
Yeah. Another thing too is they were describing these conceptual designs and models of a proposed propulsion, a futuristic propulsion type of craft.
I noticed.
Who better than FX Models, Mark, who's done extensive work with so many different organizations, military personnel, etc., and of course in media itself, entertainment, and that's part of their wing. They have their entertainment wing.
It's true, and of course with Doug, he's the legend of special effects, for crying out loud.
Exactly.
So, he's the legendary guy, Academy Award winning guy. So I think that it would be a good fit. But you know what? No matter what we see, they have to see it. Yeah. And if they don't, they don't. And that's okay. There's no harm, no foul. It's just like I want to see all these efforts out there. I want to see them succeed. I want to see CubeSat succeed. I want to see Dave Schock and that team. I want them to succeed. Mm-hmm. I'm not competing with them. I'm working with them. I want them to succeed. I want other people doing kind of what we're doing to succeed. Because the thing is, we want the answer. Yeah. We don't want to be the ones who own the answer. We want to get the answer for all of us. Right. And that's a very different approach. Some of these groups, like, they circle their wagons and they try to become, the owners. They want to be the instigators. Okay, it's going to belong to us. We're going to have all the UFOs in the world.
Right. Well, what I say is that they have, in order to find the answers, in order to be able to share the answers, you got to let your ego go. You can't be doing it because, hey, I want to be the one to discover it. I is the wrong operative word. We want to discover it and work together. Right. Yeah,
that's right. I totally agree with that. And I think in the beginning I was guilty of thinking, and I didn't really say this publicly, and it lasted about 14 seconds. I thought, wow, if we could find UFOs and we could own this data, boy, that would be something. Then I thought about what I was saying. Okay, I'm human. I went down that path and thought, and I said, wait a minute, you know what? This is the wrong approach.
Mm-hmm.
If I try to limit it to just what I know and just what I can do with my little team, my, I said, I'm saying the wrong word here. And just like you said, it's got to be we.
Yeah, absolutely.
And you drop all the pretenses, you drop all the titles, you just say, look, we're going to make this all happen. We are going to do this, and we are all on the same team. And since doing that, I've actually a lot of stressors, a lot of potential stressors have just sort of melted away, because now it's a matter of trying to just get it done for humanity and just let it go at that, right?
That's what it has to be. It has to be, and I'm talking about we on a worldwide scale. We can't be fighting against Russia to get it first, or China. It has to be something that we do together.
That's exactly right, and I agree with that 100%, Michael. Absolutely 100%.
And the thing is, with Mark, they get an astronomer.
Yeah,
they get this aspect as far as the special effects, the entertainment, and they get everything else. They get the on-field investigative research. You're getting so many different components. Mm-hmm. I think it's a no-brainer.
Well, actually, it's I appreciate that, Bill. And I'm humbled by your confidence, and I would certainly strive not to disappoint. But I can tell you this: you may see it that way, and Michael and Julia may see it that way, and I might see it that way, and Doug might see it that way. But DeLonge and his team have to see it that way, and they have to say, to them, they have to say, this is a no-brainer, right, in order to start that process to include us, or some of us. Look, if Doug gets on the team and I don't, I will be just as happy. Mm-hmm. Okay, because Doug's a big name, and Doug would draw, but honestly, what would end up happening is Doug would then come to me and say, okay, let's do this, and I'll be part of it. So either way, I'll be part of it. I don't care. It's just that we got to get it done because all of us want the answer.
Yeah.
And I think that's very important too. And Michael, you said it before, which is very important. You got to drop the egos. You got to just put me, my. You got to put that away.
Yes.
At least for this thing, put it away. If you want to look in the mirror and say, look at me, down the line, well, fine, you could do that. But for now, drop the pretenses, you're right, and become part of humanity. Be willing and accept the fact that you are one of the many, not the only one,
right,
not the elite of the few, elite of the few. It's like you're one of the many. As we've heard before, the needs of the many outweigh the needs of the one.
Exactly.
Right? And yes, I borrow Star Trek, but hey, you know what?
It's true. It really is.
Yes. I agree with you guys.
And you need a diverse team. You need a diverse team of people with different skills.
Oh, yeah.
Oh, yeah.
I don't have all the answers, Doug doesn't have all the answers. Together we have some good answers, but our science team has more answers that are wonderful, and couple all that with DeLonge's team, and maybe that's a super team. I don't know. Maybe it's a recipe for disaster. We don't know. Mm-hmm. We have to work it all out and see if it'll work. And I'd love to know and love to see if he would like to open that dialogue. I would love it, because then we could actually sit down. We're all motivated to do this. We're not so wrapped up with everything else that we're not going to devote tons of time to this because, well, frankly, we already have, So, and it's not going to stop anytime soon.
No, you're right. Well, it would be really cool to have that. Julie, I think it would be really great to have a Skype, roundtable. That would be really cool with a lot of people.
DeLonge?
Well, if he wants to come,
you think he'd come on the show with us?
I don't know. I've got open spots. We'd like to hear what he has to say.
I actually contacted them on behalf of KGRA,
Oh, yeah.
And I'm
Yes, he
waiting
did,
for a response.
Good.
Yeah.
Yeah. How long ago?
Today.
Oh, today.
Yes.
Okay.
And that's pretty cool.
I contacted him yesterday and wrote an email to him using their contact form on their website because that's all I had for an email address. And they wrote me back saying, "We're not accepting proposals at this time, but you can like us on Facebook." I mean, that kind of thing is like
Lovely.
Well, you know what it is? They got someone, maybe an intern, who's just reading it and not paying any attention to what it is.
Yeah.
And so they're not passing it along, perhaps, or maybe they are. But I think that someone could get in a lot of trouble for passing something by that might actually be good for the project, and
right,
and not doing it. Not looking at it at least.
So Tom DeLonge, he did say publicly at some point that he was an abductee or he had contact.
He had an abduction experience where he had missing time. I would tell you about it, but it's too long.
It's a whole show. Yeah. Okay. All right. I don't know.
Fair enough.
Yeah.
Story. I just know.
Well, Tom, if you're listening,
yeah, come on.
We're here and be happy to have you. We'll have Mark come on, and Bill, of course, will be sitting at the table, and we can talk about it. We can just, shoot the bull and see what's happening, and if you'd be interested in, joining the whole community.
And speaking of a roundtable, since we've got Mark on for a couple more minutes, Mark, we still are planning to have a gathering here. You want to fill them in, Mike?
Julia and I want to do a live on-the-spot show at one of the Skywatches. And,
on location.
Yeah, on location.
Oh, cool.
And we're looking at either the last weekend in.
Well, you know what? I got a date. I was looking at the calendar.
Oh, good.
I don't want to do it Thanksgiving weekend because I'll be drunk.
No.
Okay. It might be more fun that way.
I have family coming like Thursday, Friday, Saturday. So December 2nd, that weekend, the following
that might be good.
Works great.
So maybe, Mark, if you're free that weekend on a Saturday, you're welcome to stay here.
So you're going to do it at your place, Bill?
Yes.
That'd be cool.
And then you could stay over. We're there. They'll stay over, and we'll make a nice dinner, and we'll have a nice fun night doing a Skywatch.
Sounds like a plan.
Oh,
And I'm going to do a massive I'm going to do a meditation to bring them on because they come when we do meditation every time. It works for me, so I'm crossing my fingers.
I'd love to see it.
Yeah.
And then during the Skywatch,
Julie is my secret weapon.
You guys will actually sit down with Mark, and maybe I'll get extensions and put the microphones outside and put a secondary camera, and I'll be inside making sure everything's working on this end.
Oh, and sure. You're going to be inside the warm, and we're going to be out in the cold. I get it.
Or we'll all sit around here inside and let the camera do its thing.
You got to give me hot chocolate.
Oh, yes.
With whipped cream and some vodka.
Well, we'll have fun, but remember, we're going to be...
That's the oddest combination I've ever heard.
No, the vodka will have tonic.
Oh, okay.
But
I was wondering what was going on there. Maybe I was thinking, what was that for? Like to like a rub down or something?
So yes, Mark, and hopefully you'll be able to attend. It'll be, what was the date? December 2nd, Julia?
Yeah, I think December 2nd works. That's Saturday.
Yes.
December 2nd, the week after.
Thanksgiving. Works for me.
Okay.
All right, well, I'll check. I think that I actually December 2nd sounds like something I should know about. For something else, so I'll have to make sure that it's not like a Navy deadline or something else. So I'll have to.
Okay.
I don't think it is, but
you'll let me know anyway. And by the way,
I know.
For the listeners, you really need to go to Sky Tour live stream. That's Mark Dantonio's YouTube channel. He has the observatory in front of his home. He takes just amazing photos and video of the sky. Tell us a little bit, Mark, about what you do with Sky Tour.
Yeah, please.
Thank you for the opportunity. The Sky Tour live stream was something I started on the behest of Bill and Paul and Keith from P&K Space Imaging. And basically, as an astronomer, I've always been in tune with the sky. So I've always wanted to bring astronomy to the masses. And what I'm doing is I have a nice, very sensitive camera that I've modified to show the night sky and show very faint objects in the night sky almost instantaneously. So we steer to it, bam, we can see it. I can record the sky that we see, which is streamed out as well in full 4K video at various sensitivities up to over 400,000, sensitivity, 400,000 ISO, basically ASA for the old timers like me. And we actually show these objects in the sky and we discuss them. The other day, for instance, we looked at planetary nebula, which were dying stars. And I talked about the little tiny white dwarf that's in the center of these planetary nebula. And I talked about what makes a white dwarf and why it doesn't become something even more compact called a neutron star, and something even more compact called a black hole. And I talked about why that all happens. So it's like I take people on a tour of the night sky, show them the different objects, and then we discuss what we're looking at. And we discuss why it looks the way it does, why the colors are what they are. And I do it in a way I think that people understand. I hear that people actually understand what I'm talking about because I try to put it in terms that everybody can understand, because everybody wants to know and they feel it's out of their reach. And I just don't believe that's true. I think that once people understand, then they can take it further on their own. So Sky Tour live stream is an outlet, a place for people to go to watch the night sky unfold live. The chat room, the people can join the chat room and they can talk back and forth. My moderator, my primary moderator in Sky Tour live stream is Amanda Curran. She does a wonderful job, fielding all the people from the chat and running the questions through me, because I'm doing 5 things at once in the observatory. So I can't look in the chat at the same time because the chat is actually a bright white screen and I'm in red light in that observatory. Right. So I can't look at these bright screens because that ruins my night vision. So Amanda fields those chat questions, gives them to me, and then people also have requests. Can we see this right now? Oh, sure. I'll steer to that right now. We go to it. Bam. They see it. Huh. So it's really cool. It's like a astronomy on demand sort of a thing.
Love it. Yeah.
And people love it. They really like it.
And Amanda also helps Mark. She's the one that pretty much came up with the idea for the Facebook page, Sky Tour Livestream with Mark Dantonio. And
she did it on her own without even asking me, and it was the best thing she did. It was like a wonderful birthday present kind of a thing, even though it wasn't my birthday.
Oh, wait a minute.
Well, it is.
It is Tuesday. Happy birthday.
Yeah. That's right. Happy birthday.
Oh, yeah, you're right. It's the 14th. I forgot my own birthday, and I wasn't baiting you. I swear to God, I didn't know. I forgot.
Does anybody want to try to sing? I'm not.
No.
Happy birthday.
Oh, boy.
For the listeners.
If you ask me, I'll have Clem sing, and you won't like that.
I could give you guitar accompaniment, but,
Oh, that's cool.
We could jam here.
I have a music studio and a broadcast desk here, so yeah.
Mike, I got the drums here. I've got the guitars and everything.
Oh, I'll bring mine.
But just before Mark gets to go, because we got about 20 minutes left of the show, you can see some incredible photos that he takes. It's posted on the Facebook page. So if you go to Sky Tour Livestream with Mark Dantonio on Facebook, Amanda or Mark or some of us that are administrators will post. There's a lot of people that contribute to the site, to the Facebook site. So definitely go check that out. You'll see, stunning photos.
Well, I use some special techniques to actually do image processing on them after the fact. And I use a technique called stacking, which is common in the astro world, where you take, say, 24 of the same thing, so the same exposure, the same length of time, same sensitivity, and then you stack them digitally so that all that data gets added together. And then you take these what are called dark frames, and so where the background is getting brighter and brighter and brighter as you add all these together, the dark frames allow you to get rid of all that that background that doesn't belong, and all you have is what we call the quote unquote signal, and the noise goes away, and it really increases signal to noise in a picture. And signal is what you want. Signal is the data that you can see and make sense of with your eye. Noise is just static, and that's not helpful. So stacking helps that. So I show people how to do that, and on a cloudy night, sometimes I'll actually stream. And I did a cloudy night stream a couple weeks ago, Bill. I don't know if you were there for this one. I took people through the Lunar Reconnaissance Orbiter Quick Map feature. Now, I don't know if you're familiar with the Quick Map, but the Quick Map is a site that's run by the Arizona State University, right, ASU. And what they did is they have all of the Lunar Reconnaissance Orbiter camera, LROC, data up there. And it's the entire moon, front and back, okay? And you can zoom in to a level where it's only where it's as tight as 0.5, half a meter per pixel on the camera. So you can see rocks that are about a meter across.
Man.
Okay, on the moon. Yeah. So that's really small, and you can see that for every nook and cranny on the entire moon. Now, that is really important for the people that want to look for these lunar anomalies. If they think there's anomalies, well, then go to the LRO Quick Map. You know, you look it up like that, and you can just go there. It comes up in your browser. Bam! You can go down and you can look at this particular area, and you can see that no, Pythagoras Crater doesn't have a giant gun in the center of it. Right? Pythagoras Crater has a strange mountainous region, but you can zoom into it so far that you can see gullies and slopes and material that's slid down the slope and rocks actually that have left rolling paths, down the central peaks of some of these craters. So, I
guess it wouldn't be hard to see the other Apollo landing sites either.
I was just going to say, if you click on the left side, there's a whole list of all the additional features you can select from. One of those features is LROC featured images.
Cool.
And you click on those, bam, there's the Apollo landing sites. You can zoom in, you can see the landers, you can see all the tracks from the rovers. You can see the American flag in some cases.
Oh my gosh.
Yeah.
Cool.
And people say, can you see the American flag with the Hubble telescope? Well, no, the Hubble's in Earth orbit. Okay. And the American flag on the moon would correspond to a fraction of 1 pixel on the Hubble sensor.
Yeah.
So we know that pictures are made up of many thousands of pixels, right? An image that makes any sense has to be made of at least 320 by 240 or 300 by 200 pixels.
Uh-huh.
And we can't have a picture that's in a fraction of a pixel because a pixel is just one color. Okay, so the Hubble can't see that with that kind of resolution. Yet, people think, well, it looks at all these very faint objects so far away, and they're confusing distance to very far objects as being a requirement to see, very, very tight detail on the moon. And they're two totally different concepts, two totally different capabilities.
Wow.
And the Hubble doesn't have it. The James Webb Telescope goes up next year, and that has a mirror that's 21 feet in diameter to the Hubble's 8. And we're going to be able to see planetary atmospheres around around stars, around exoplanets. And I'm so excited about that.
Yeah.
See, it's all coming. It's all coming, guys.
Well, see, all you moon landing doubters out there, check
there.
The
Quick Map. Yeah.
It is. Yep. And you know what? If you start looking at that, Michael and Julia, you guys, you'll get totally lost. You'll end up spending like hours. You go, wow, I had missing time.
That's what I had.
Not really. The LRO browser did it.
Hey, Mark, did you hear about the new announcement? I don't know if it's real or not, but I saw it a few times on Facebook that NASA discovered something. It's like the first time they ever saw it. There's like a new announcement, and it's
I saw the press. I did see the press brief on it, and I didn't actually get to see what the actual announcement was because they said they're going to make the announcement like a couple days ago.
I think it's Tuesday, Mark. I think it's going to be Tuesday.
Monday?
Yeah, it's one of these upcoming days. Yes.
So that's unprecedented, but it wasn't they already know about the sphere, the megastructure around that one star.
The Dyson sphere? Yeah.
Tabby star. They think that it was it's actually they're saying that they think it might be an actual cloud of dust.
Yeah.
That is passing between us and the star. But the fact is there's no overage of infrared radiation that you'd expect to see. So maybe they're looking at it in a different way. or maybe they're looking closer to, maybe it's closer to the Earth than they actually expect it to be. I don't know.
Well, they make it so exciting, and then it's like, you know, the mega structure was exciting when they first talked about it, but you know,
yeah,
I'm expecting some. You know, they make it so exciting, then it's like, oh, okay,
well, it's actually it isn't actually NASA that ever said it was a megastructure. It was actually people that were speculating about the NASA announcement.
Yeah.
It was actually, see, Tabitha Boyajian is the one. She's the one who was doing the research on Tabby Star, and Tabby Star was just a star that was part of the Kepler retinue of stars, program stars they were looking at, and Tabby Star as such was one of the many, one of the 100,000. However, when Tabitha was looking at this star, she noticed that there were some strange dimming events that couldn't be explained. And that was in the Kepler data. But then they discovered that the star has been doing this behavior for just over 100 years.
Well, couldn't they be, if it was like an energy structure, couldn't it be pulling the energy, like maybe an alien race is using that star for its energy?
Yeah.
Unlimited energy. So it's pulling it. That's why it's
right. Yeah, Freeman Dyson, had postulated about the Dyson sphere years ago.
Yeah.
And of course, we know the Dyson sphere. We've seen it actually in a Star Trek episode, for instance.
Yeah. But
the Dyson sphere was, it's basically is a structure that surrounds the star entirely, so that the starlight and all the energy from the star hits some element of the sphere, which that population can then use and capture. Now, the problem with that is, of course, that a star is a massive thing. And to build a structure around the star would require more materials than any solar system ever has. It would have to be a monumental structure. So, in other words, they would need the kind of energy that a population, or a Type 5 population on the Kardashev advanced scale would have to do Type 2 kind of work with a Dyson sphere. And
I can imagine it would take several lifetimes to do it, a couple of hundred years.
Well, if you have a race that's a billion years ahead of us, and they can create metal, they can actually create what they need.
Well, sure. And I actually postulated, and I think it'll come to pass. When you think about the concept, and I know I keep going back to Star Trek, but the bottom line is Star Trek has been replicated throughout science.
Oh, yeah.
Okay.
Yeah.
In some ways, obviously the cell phones, okay. However, the warp drive as well. Now, not the same way as in Star Trek in Roddenberry's mind, but the Alcubierre drive was something was postulated in '94 to get us from here to there in a very fast way, and that is to say, by basically warping space, folding space. Okay. Now, that process, okay. That was called a warp drive because that was actually something Alcubierre did in deference to like Roddenberry in part, but also because it really is a warpage of the space-time fabric. Space-time fabric's a mathematical construct, but if you think about it as a way to get from here to there without actually moving, okay, you actually when you have that warp bubble around your ship, you can actually basically you're pulling the universe past you as fast as you can,
right? And
you're not limited to light speed at that point. You can go 10 to 100 to 1,000 times as fast as light, because you're not really in the constraints of our four-dimensional universe, X, Y, and Z, all moving through a time period. So if you could do that, then you could actually make your way through the galaxy fairly quickly, or through to the nearest stars anyway. We could get to Alpha Centauri, and technically we could get there in 5 days with this drive.
Wow.
Not 19,000 years. Yeah. Whoa. Not 19,000 years like it would normally take. But when you travel down a highway, you see that over time you get bugs on your windshield. Well, space has bugs on your windshield too that you get on the front of your warp bubble. And those bugs are in the form of charged particles and other detritus that builds up, mostly energy type events. And so when that happens, when you stop your warp drive, all that stuff sloughs off in a very energetic, explosive way, according to the way the Alcubierre tensor describes. And if that's the case, it could potentially destroy any solar system you're entering into. So the realistic time frame to get to a star like this using that kind of a drive is like 2 to 3 weeks, because you start slowing down and bleeding this stuff off this warp bubble little by little. It's a very, very complicated process, and it requires something akin to negative mass, which doesn't make any sense to most folks. So it's like we're probably about, I've been saying, like 100 years away from a Coke bottle probe using the Alcubierre principles.
That would be so cool.
Yeah, but because NASA has reworked, through White, that scientist White down there, they reworked the warp drive generating system on the ship to the point where it doesn't need this obscene amount of energy, which is the equivalent of converting Jupiter to energy. Right. But it only needs the equivalent of the Voyager spacecraft converted to energy. Now, that's like a 10 to the 26th power drop in the energy requirement, and that's what made it attractive to NASA. Now they said, oh, this might be something we could do. And so they've actually funded a lab, to look at it. So you see, the future's coming at us. It's being hurled at us by the universe, and little by little, we're gonna start to be able to, interpret it, understand its rules and its regulations. We already know how to go faster than the speed limit in the universe. We just have to be able to actually do it, and the technology is coming. We're going to reach that point, and that's going to be a wonderful day.
Oh yeah,
yes, it
absolutely.
will.
Tom DeLonge, I hope you heard every word Mark just said.
Okay, Tom. It's in your
Tom.
the ball's in your court, Tom.
For real,
ball's in your court. So, well, anyway, it's getting close to that time, isn't it? Mark, thanks for stopping by. Really,
yeah, sure.
Great.
Yeah, thanks for having me.
It's always good to have.
Total surprise, but I'm glad that you were willing to have me come out for a little while.
Very cool, yeah. And of course, thank you, Tom Reed, for spending 2 weeks with us and sharing all of that information about your experience at Paroween, which ought to be unbelievable.
That's Salem, right?
Yeah, Salem this year, right.
Mm-hmm.
So next week, we're going to have a gentleman by the name of William Lawrence, who has developed a way to communicate with aliens using visible light. So that will be a very interesting program. And on the 28th, we're going to see Grant Cameron again, talk about his new book. And on November 4th, an old alumni of the show, Susie Byler, is going to be coming. And that ought to be a fun show, too. She's awesome.
Yeah, it's going to be a lot of fun. She said she felt led. There was more things that she wanted to, that came to light. She'd like to talk about. Yeah.
That's good. Okay. Guys, thank you very much for joining us. Audience out there, we'll see you next week again. And once again, Mark, thank you so much.
Thank you for having me.
And I'm always learning new things when you come on the show.
Hey, you guys are great. Thank you so much.
No problem. Bill, see you next week. Julia, see you next week,
everybody. Love you.
God bless everybody.
All right. That's the Starborn Connection show. And now, so I can eat my dinner and enjoy the screen, I'm going to play the post-commentary after today's conference when Mark joined us. And Mark can give a little explanation. Amanda was with us. So I'm going to do that now. Hopefully.
What it was that was special about having LIGO involved, because in terms of seeing all of these.
Okay.
There have been many observations of.
Let's forward a little bit.
I'm going to take
one more question.
Advance.
This for a while to come. Thank you.
Here we go. Okay, we're back, and with that, I want to say Einstein is somewhere smiling. Somewhere,
I think you're right.
The thing I caught off this, Mark, and I know you have probably a lot to say about this, was the multi-messaging and the correlation with all these different observational platforms coming together to validate one each other through all the different spectrums. With, of course, because of LIGO and Virgo capturing this, they were able to ascertain it and get to it almost instantaneously. Now, the one thing I did catch, they need to definitely come up with a better system of an alert system that these electromagnetic sources, these other observatory platforms that with using light, can get on the object sooner when LIGO or Virgo detect it. And another thing, for people like you, Keith, and other amateur astronomers, myself, they should make a public app by LIGO or Virgo to notify amateur astronomers to, hey, we've got something going on. Almost instantaneously sent that alert out so people could all focus all over the globe and look at this object.
Yeah, it's easy. I'm talking to a iPhone developer now who's actually going to possibly help us do a aerial anomaly detection system, formerly UFOTOG 2 application. So I think that's very, very possible, and it's really not hard.
Exactly.
It's not hard because that information is available on their servers. You already know when they're coming out. They just have to make it public. That's all.
Exactly.
Making it public is the big deal.
Yep. And giving access. And you had that person say, well, what was the significance of LIGO and Virgo? Why, with the gamma rays and X-rays, whatever other array that they were talking about, why was that so important? Because it was neutron star. They were the twin neutron, the merge, and that set off all of them to now get to that area in the sky and all correlate the data. And that's what I think the significance of this conference is. Everyone coming together on all these different platforms to correlate the data that was coming in from LIGO and Virgo to say, wow, we all seen it too.
Yeah, no, I agree.
On that note,
some
people were coming in and missed the first part. Can you just recap the two panels, what we saw, what they were discussing, what happened? Just to catch everyone up before we get to it in detail discussing it.
Okay, yeah. I mean, Bill's been taking lots of notes, and I can tell from my perspective what went on. But
go for
just
it.
What was the conference all about? What was the big announcement? Yeah. And what do we know?
The LIGO interferometer is a device. There's two of them in the United States. One's in Louisiana. One's in Hanford, Washington. And it's designed to actually detect gravitational waves. That is, the resulting waves produced by large-scale cosmic events like merging neutron stars, very large supernovae, and then the Virgo interferometer is another instrument that's also designed to detect the same thing. And the problem is these interferometers are ground-based systems that are very large, and they only have the view of the sky above them, basically. So they have to wait for the Earth to rotate into view before they get the event or see the event. So having a network of them around the world will help us see any of these events that occur. And because the events last over a few days, brightening and then dimming, we get a chance to actually see them with other instruments. And if one sees them, sees an event, then the others can come online and say, oh, we're going to be seeing this event in like 4 hours when it gets dark, blah, 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 or whatever. So the bottom line is this announcement was about the fact that we've seen these gravitational waves and that they are really the first time that we actually saw merging neutron stars create something predicted by Einstein but never before seen. Mm-hmm. Now, they talked about them before, but this is something that's a little bit more spectacular because this one also included an optical event. Now, optical meaning in the spectrum of light that we see with our eyes, basically. Typically, gravitational waves would be detected by other means, elsewhere in the electromagnetic spectrum where we can't see. But this one actually had an optical counterpart, something that you saw. They showed it on the screen, and when you go back and look, you'll see it. You saw a bright spot that was actually blue, and then it faded to red over a few days. And that's because it was high energy at first, and as the energy waned, it went more toward the red, as expected. So, that said, this event was really quite spectacular in that regard. And it also confirmed a few things. It confirmed, for instance, that the heavier elements in our universe are created by these merging neutron stars. And if we just happen to see one of these events now, then who's to say that they don't occur far more often, but we just don't see them or just haven't been looking? And so that's something that is very important to consider as well. So if we see them in our puny short lives of less than 100 years, then in the universe's existence of 13.8 billion, this must have occurred quite a lot and must be occurring quite a lot. In fact, several events a year occur. And that adds up to quite a few over the course of 1,000 years, 1,000,000 years, 1,000,000,000 years. So more than enough to populate the interstellar medium with the materials needed to make planets around a forming star. That's where we came from. That's where all the exoplanets we see came from. Their materials come from these types of interactions. And it's not only merging neutron stars where we find these elements being made in our periodic table. They're made in planetary nebulae, which are fairly docile endings for stars.
Supernovas, Mark?
Yeah, well, that's next. I'm just going to get to that. So they come from, these planetary nebulae, which are the expanding outer shells that kind of made their way away from the star as it began to contract away from the outer layers. And those became, clouds of gas and dust and other stuff that became part of the periodic table eventually. And then in supernovas, like Bill's just said, a star that finally explodes, leaving behind potentially a pulsar, which is a very, very hot core that rapidly rotates like with hot spots on it that if we see them, they pass us and they go by us and we see them. Some are optical, some are not. And we can see these things a lot, in the night sky, not with the Sky Tour live stream telescope because it's not nearly bright enough, to see it that way. But the bottom line is that when we see these, elements being created by supernovae, that's another way that we make some of these elements. But how the heavier elements were made was outside of the understanding because we would just say, well, maybe they're made in supernovae. But then you could tell that there was a lot of missing science, a lot of gaps in how that could possibly work. And it turned out that if you said, well, what about neutron stars that are merging? We think perhaps that maybe they're made, we get elements that way. And the answer is that we do. And that's the other part. So there's a number of ways in which these elements are manufactured in our universe. But
Mark, but with the merger or collision of the neutron stars, that's by a much higher volume of the release of these heavy elements, correct?
Oh.
In other words, they're throwing out when these mergers or collisions happen. It's a much larger release of these heavy elements in comparison.
Oh well, yeah. Yes, of course, Bill. Sorry, I didn't hear that.
And the thing is, until they start getting more data on other colliding, then they can pretty much use that to say, well, this one released more or less. They need more. You can see that's what they were mentioning. And by upgrading, and with the upgrade that they're doing for the year, they're going to have eightfold what they're going to be able to collect and ascertain.
That's right. And the nice thing is, this event was something that had the energy of 1 billion trillion suns, as they talked about.
Yep.
Well, a supernova doesn't have that kind of energy. A supernova is pitiful in comparison to the energy output. So this is a rather rare event. It's not like it's an everyday event. Okay, but these events do occur at various times in the year. In the same way, the universe always throws something strange at us. During the course of a year, not a year goes by when we don't find out that a massive meteor came through the atmosphere. The one in Russia that smashed windows and hurt people. Mm-hmm. Then there was one before that and one after that, in fact. So we have a lot of these events. So, along with all the noise, that is, all the regular events that we see, we do have these occasional and sporadic, spectacular events. And that's what this was. That's what this was, and I think this was a very interesting conference. I actually liked it quite a bit. I really enjoyed listening to everything that was going on.
Same here. I mean, I was like you mentioned, I was writing down notes as it was going. I found it so fascinating, and I think it's great to have this collaboration on a global scale. While everyone's bringing their data together instead of, these individualistic backed corporate groups doing their own. It seems like it's coming together, and I think that was significant to see all the different observation platforms coming together and putting their data into one.
I agree. I think it's a rather impressive array of scientists, including Alessandra Corsi, who is one of my relatives. Actually, I believe she's actually the great granddaughter of one of my Italian relatives.
Wow!
Because my aunt was Josephine Corsi.
Now,
William Corsi was.
I got a question for you, and I was just thinking of this as we were watching. How long? I mean, and I know it's quite a bit of time to do this. How long would it take, say, for the Webb telescope that's going to be launched in the next couple of years because it's been delayed?
2018 coming up.
Yeah. How long would it take to navigate that to an area of the sky where some activity is going on, Earth-based, or even on our satellites, like they mentioned, Fermi and Integral, etc.? How long would it take? Yeah. How long would it take to maneuver it to go into a position where it can collect the data? Is it too long for it to do it, or would it take hours, days?
I don't think so. I think that, just like with our Hubble, I mean, the Hubble was retasked, as an emergency, to actually check this object out. So, the Hubble's up in orbit. All it has to do is use some of its power to, spin up the wheels, the control wheels that actually they use instead of retro rockets these days. And the wheels are basically think of them as a bunch of spinning hard drives at odd angles on board the satellite. And as they spin, they change the rotation rate very slightly, and that torques the satellite over using the torquing and physics effects on the satellite, which is, of course, weightless in space. So it wouldn't take long to reorient it. It would just take it'd probably take longer to get through the red tape to say, can you please get off your object you're looking at and go to this object? But I suspect that'll happen. I suspect you're going to see that quite a bit, with the Webb telescope. Because as we learn more, we realize that the information we're getting shows us so many new things in so many new ways that it's absolutely impossible to keep up with. And they mentioned it. They even said it's so hard to keep up with the developments. And when you see once every few years, one of these events, you can handle that because the science takes several years to study just one event. But when you see 3 or 4 a year, now what, right?
They said they loved all that work. they were welcoming it. Bring it on, pretty much.
Yeah, well, yes, and he said, it's a good problem to have.
Exactly. And another thing I noticed in the first panel, they were showing a video of a space-launched gravitational, an array of satellites, it looked like.
Yes.
Can you get do you have any understanding, or can you give us a little explanation about why that would be much more maybe significant than having it here on the ground?
Well, sure, because on the ground, the interferometer, the way it works is it has 2 detectors that are separated by a few miles. In space, you could separate your detectors by hundreds of miles and not have a curve of the Earth to worry about. See what I mean?
Yep.
And so you might actually be able to have this large object out in space that can detect these more distant events with higher resolution. And that's actually significant. That's very significant. So, I actually hadn't heard of that project until today. But then I realized, hey, you know what? That's a far better way. That's a far better way to actually study gravitational waves than to just have a interferometer on the ground. Because, in the same way that when we study distances to stars. That's called the parallax program. I was in the parallax program. When I got my degree, I spent several years in an observatory photographing stars that were considered quote unquote nearby, and the stars would be viewed against the background of further stars when the Earth was at each end of its orbit. And those photos showed a tiny shift in the closer star because of parallax. That is, when you extend your hand at arm's length and you blink one eye and then the other, you see that your finger seems to dance against the background of the wall or whatever's on the wall in the background. Mm-hmm. That's parallax. Consider your finger to be this nearby star and the wall to be the more distant stars. That angle it makes, we can calculate what that angle is, and that angle tells us the relatively exact distance. I like that, relatively exact. The close to the exact distance of the star. So in the same way, we're limited by the size of the Earth's orbit.
Was that why
we don't have observatories, on other planets with larger orbits? Okay, and if we did, we would have to wait a very long time. Now, when this other satellite goes out to, they were talking about a point where the gravity of the sun and the Earth balance. That's called a Lagrange point. Mm-hmm. Well, if they go to a Lagrange point, then the object that satellite might actually be, it could be farther from the Earth, or it could be closer to the sun. And you would say, well, wait, how could the gravity of the Earth and the sun balance if it was farther from the sun? Lagrange points work funny ways. Okay, you actually have some Lagrange points out there that are strangely placed. But if we actually were to put them, say, out a little farther, and put something in Lagrange orbit that's farther from the Earth, past the moon, more toward Mars, then we'd have a much larger baseline, and then we could accurately, get parallax values for stars farther out by a lot farther. Mm-hmm. So, in the same way, an interferometer that has a 1 or 2 mile baseline, okay, where it between detectors, is great, but it's on the Earth, and it can't be too far away on the Earth because the Earth curves, and we got all kinds of problems with visibility and so forth. But if you have an object that is out in space, you can actually increase the size of that baseline kind of on a daily basis. You could say, okay, let's go to this distance today, and then come back to this distance tomorrow.
Yeah, because they even mentioned that they had blackout areas when they were collecting the data, and even even with the satellite with the gamma, because the jet wasn't facing directly, it was off at an angle. That's why it was a little difficult to discern it exactly what it was, because it wasn't that much different than some other gamma ray activity coming from objects. And the thing it was so interesting when they were discussing this, because I think that when they expand this, and especially with the space observation platforms, and just to get all this information, Mark, and to put all these people on the same trajectory and the same path, it's going to be fascinating to see what's to come. I'm excited when I was watching this. I was like, wow.
So am I. I think it's going to actually be a very impressive era of astronomy. And they're talking about it like, well, this is the era of gravitational wave astronomy. Mm-hmm. And it is a significant time because for the first time, we're actually getting a handle on the phenomenon of these gravitational waves. And I predict in like 40 years, perhaps 50 years, we're going to start seeing theories about how we can actually defeat gravity and how we can actually do an end run around gravity in the same way that we can already see how to do end runs around light speed. Okay, so I think that's all coming. And so if I could have chose when I was born, I probably think if I had to choose like a time slot to be born in, I probably would, right on the heels of this one, I'd probably wait about 100 years and then do it again.
Yeah,
just to see.
Exactly. Another thing, Mark, I have a question from. I was thinking about this. Does the jet, when it's putting out this energy, does that jet necessarily need to be in our direction to detect these neutron stars colliding? Is that a proponent that's significant, or it's just based on other aspects of detection?
Well, we actually got kind of lucky with this. It wasn't exactly on the angle to us, but it was enough so that we could actually see it. But there are neutron stars that have gone through this probably that are, circling each other at, flat planar directions so that we would never see it. And maybe we've missed them. Maybe we've missed hundreds. Maybe we've missed thousands. Who knows? Maybe these objects are doing this all the time in the universe. We just don't know. But if it's not, if we don't get some component of it, then we see the light from it, because the light radiates in every direction.
Right.
And we saw the optical component to all this before in this press conference. So seeing the optical component is important, because that says, all right, something happened here. In the past, we might have just said, oh, it was a strange supernova. When in fact it was nothing like a supernova. And the thing is, if it was a supernova, then it would have been really strange, because it would have gone away after just a few days. Usually supernovas stick around for a little longer. It's a very bright explosion. It's going to last for a long, long time. But these things here, they're called transient. Supernovas are transient too, just longer term. This was a transient burst as well. And when they said GRB, when you were talking about GRB, that's gamma ray burst. So,
which is exactly where I'm going. Well, not exactly where I'm going, but I made a note that they said that 9 days after, that's when they detected using the X-ray. They kind of are leaning to a conclusion that it, like what you mentioned too, is the light black hole. It seems to think that they think that this is a light black hole.
Well, actually, not everyone thinks that on the
panel. No, you can see. You can see
they're
that.
Being very polite.
Yeah, they are.
Very polite.
I noticed that.
Yeah, one woman got up there and said that, and showed in a little video, she showed the neutron stars colliding and obliterating themselves, which is what I predicted they might happen. But who knows? We don't know yet.
Even the one with what was what was the other side of the Chandra satellite? She said that we may have
Chandra, Chandra, Chandra.
Yeah, Chandra. That she said, well, we may. All right, Mom, I'm live, please. She's giving me breakfast as I'm talking. She said that, well, with our past data collected, we may have actually had numerous accounts of this happening. So like you said, you could tell that there was difference in opinions on that panel, but like you said, they were being very polite.
Well, there's science. Science doesn't naysay someone else. Science says, yes, that could be true. And they let them speak, because they not only have a right to speak, but they're not speaking falsely. The only person speaking falsely is the person on the panel who might say, oh, that isn't happening, or no, that can't be true. As it turns out, the naysayer is the only one who's got the narrow mind. And so the bottom line is here, we don't know whether the neutron stars, when they collided, that they obliterated themselves. We don't know whether when the neutron stars collided that they merged. And we also don't know whether the mass of these neutron stars was enough to put it over the edge to become a black hole. Transpired in all the data.
They gave numbers for the so collided. No,
I could be. I don't remember that part, but it could have been.
Oh.
If it was,
I think they were talking about the energy released by a supernova in comparison to neutron stars. I think that's
the thing is. Remember, there's also something here that none of them mentioned, and that's because they assumed everybody knew it, and that was the Chandrasekhar limit. That limit is 1.44 solar masses. Above that, a white dwarf can't exist. Okay, above that, a larger star that when its core shrinks down, if that core weighs more, has more mass than 1.44 solar masses, at the very least, it's heading to neutron star territory. And if it's very more massive, then it'll head to black hole territory. So 2 neutron stars that are at the low end of the spectrum, could end up becoming a larger neutron star. But like I told you, and I mentioned this earlier, Neutron stars are more like an object that has a surface on it. They're hard. And one of the scientists actually said billiard ball. That's a good analogy, right? Hard, crusty outside shell. I mean, that's what a neutron star is. So what happens when these two large objects collide? Well, what happened when the object collided with the Earth to make the moon, okay? It made the Earth molten again, it made the moon, and it obliterated itself in this giant cataclysm between the Earth and whatever object that hit us. So that said, if that happened, these neutron stars at a cosmic scale, these two neutron stars colliding, that could have been just an absolutely unbelievably outlandish size explosion. And that's one. And if you notice, a scientist called it a kilonova. Okay, I mean, kilonovas. Basically, the best way to say, it's more than just a supernova. It's a kilonova. Mm. That's kilo, K-I-L-O, nova. Mm-hmm, mm-hmm. All right, and so that's way bigger than a supernova.
The power.
And I don't know. Maybe there's a meganova that would be, somewhere behind that. Or beyond that. I don't know. But kilonova is a good term. But and kilonova suggests that what's left behind is just a remnant, not a merged, double-sized thing. Because remember, all that energy is going out there that we saw. That energy is going out. That's energy that was formerly some form of mass. Okay, mm-hmm. And because matter can't be created and destroyed. Okay, it can also be transformed into energy, and when you transform it into energy, you see this massive thing. And we saw this massive thing. So most likely, the masses left behind at the end were far less than the masses of the progenitor neutron stars that actually caused this. And calling it a neutron star is kind of a hard thing to grasp because they're not doing nuclear fusion like our sun's doing. Okay, and a white dwarf doesn't either. The only thing that a white dwarf has, for instance, and a white dwarf is the less massive counterpart to what a neutron star would be otherwise. Okay, if the neutron star originator didn't have as much mass, it might have made a white dwarf. Well, again, you have this degenerate material on the surface and throughout the star, but there's no nuclear fusion going on in these stars. They're really just they're really just generating a lot of thermal energy left behind. Mm-hmm. Remember, that thermal energy really doesn't have anywhere to go, right? It can just radiate. And of course, over time, radiation will reduce the temperature, but there's no conduction like into the air to heat the air, into the ground to heat the ground. There's nothing like that there to really wick away that temperature. There's no heat sink, so to speak, to take away the heat. So it only has the space itself. And people say, well, space is cold, right? No, space doesn't have a temperature. There's no definition of temperature for space because that depends on a medium through which temperature originates. Okay, there's no medium in space typically for what we're talking about here. So neutron stars will remain hot and for quite a long time. And if that temperature wicks away over time, then that's one thing that can happen, but it's going to be billions of years. They may outlast the universe. In fact, if the universe disappears in 20 billion years, maybe these neutron stars will say, hey, where'd you go? So I don't know.
And just for the listeners,
yeah?
I didn't mean to interrupt, but for the listeners, this is Mark Dantonio, astronomer. He has an observatory in the front yard of his home. This is the kind of experience and knowledge and educational information that you will get at his YouTube channel, which is Sky Tour Livestream. So he will do exactly this as he's doing a live presentation, whether through video or photo or other kind of maybe a software display using various kind of things that he has access to. Well, this is what you get at his channel at Sky Tour Livestream. So if you really want to get this kind of knowledge-based information in regards to sky, celestial events or locations, constellations, nebulas, etc., you really need to check out Mark's channel. And this is just a little snippet of what Mark does on Sky Tour Livestream.
Well, wait. Usually, I have the observatory open. The telescope is pointing at objects in the sky on clear nights, and we actually talk about all the genesis of these things and where they came from, where they're going to. And it's really much better to talk about these things when you actually have something in front of you.
Exactly.
That's real. It's the real thing.
Yep.
And that's what we do. Yeah, you're right. Thanks for that, Bill. That's nice.
Also, Amanda, are there any questions coming in from chat that you may have jotted down, or because I can't see chat because I've got my screen on full. I'm on full screen on my end, so I'm not seeing chat. Anything coming in? Do they have any questions for Mark?
I had some questions from the first. Well, actually, from the beginning when we were talking before the panel even started, and a few from back there. I know you've probably written a small novel, and I had a few things written down. So, what do you want to do?
No, I had my
listeners.
Yeah, let's do the chat.
Small novel.
Oh, he had 2 pages before the first panel, and I think the panel probably ended before he was done writing, so he got stopped at 2 pages. I don't think he was done.
I wasn't, and I was jotting up the second one. But yeah, let's get chats.
This
questions.
is why you are such an incredible host, because you do your research and you take notes literally, and you get the right questions to ask, and you find the right people to ask them too.
Well, let's get chatting. So, let's ask, because some people may have just joined us now and they didn't catch the first part. So let's get some of those questions.
Yeah, that's why I wanted to recap. Okay, well, way back, Rudy said he was just commenting, was Einstein the first person who talked about gravitational waves? As we heard through the panel, he obviously was. Is this basically how he thought it was going to be? What, I know that question came up actually in the panel, but could you talk about maybe where he was off, where he was right?
Wait,
where we can go from here?
In terms of the discovery?
To theorize about gravitational waves.
Okay.
Unless I'm wrong, and then you can correct me as we go.
No, I don't know. I mean, but was the question whether this panel?
It wasn't really a question. We were just discussing before the panel came on, saying, what do you think it's about? And someone just said, was Einstein not the first to talk about gravitational waves? And I thought maybe Einstein's theory what led to LIGO forming, or it was just a comment, but I'd kind of like you to explore it a bit.
Well,
more.
One panelist said we're still trying to
Bill,
prove.
Take over again.
No. One panelist said we're still trying to prove Einstein wrong.
That's right. Yeah, she actually said. And once again, Einstein was shown to be correct. And the thing is, Einstein predicted that there'd be gravitational waves, but he also said that we probably wouldn't be able to detect them. And that was sort of one way in which he was wrong, if you want to call him wrong. But how could he possibly have known?
But why did he think we would ever be able to discover them in the first place? Like, why didn't...
Well, he didn't.
I mean, we're not really talking that long ago. Like, why?
No, but he didn't think that we'd be able to see them, because he didn't think we'd have the ability. Because he knew that the gravitational wave effect was basically going to be like a billionth of an inch here on the Earth. All right, and he didn't think we'd have instrumentation sensitive enough to detect it. And of course, in that note, he was wrong, because he didn't have access to the future. So that all said, when we look at what happened here, all right, I see that what they reported. I thought this was what this whole press conference was about, because I've been following the chatter, in the back rooms, so to speak, of all these organizations, and the chatter was that there was going to be a gravitational wave announcement. What I didn't realize, and they did manage to keep quiet, was the fact that they had found not just gravitational waves using this interferometer, but they could see a visual source, a counterpart. That, you see, is very important. They've never seen that ever. And so not only did we get gravitational waves, we got a visual counterpart. And not only that, we saw a perfect correlation between the initial brightness of this thing and the fade out, going from highly energetic blue to less energetic red, and it was just really a wonderful wonderful thing. And so this was actually very much a right on track. I thought it was going to be gravitational waves. I had no idea they were going to show us an optical counterpart.
But you called it. You did call it before we even started.
Well, I didn't say optical counterpart at all. I had no idea.
Well, you said light. You did say light. That could be the spectrum of light, X-ray, gamma, infrared,
yes,
etc. So you were on it because that was, look at the panelists. They were all part of these different platforms. And so you were right in one aspect.
Well, you're just very forgiving of what I say sometimes. So, and that's okay. I mean, no, I did not predict the optical counterpart. I did not expect to see visual imagery showing this thing in NGC 4993. Okay, out there at all. But I thought they were going to have confirmations via other instruments, and they did. In fact, 100 instruments around the world they had confirmation with, and that was very, very cool. And so that was very impressive. I'm I was very happy to see that. But I know that people watching and listening right now are thinking, "Oh, so what? What's the big deal? They saw something along the visual to go with it." I know that doesn't really strike people as really important. Okay, but think about it. This panel started at 10. This announcement started at 10 o'clock, and it just ended a few minutes ago. Okay, there's a reason why it went for like several hours. All right, it went for several hours because we truly haven't ever seen this before in the universe. This is an announcement like, look, we found the planet. It's called Jupiter. It's not like it's an announcement of something we already know. It's an announcement of something we saw. And in addition, we saw the optical counterpart to it. That is the visual spectrum version showing this other part of this. That answers a lot more questions and, of course, throws up a host of many more.
Mark, what part of the sky, because I never got that clear, what part of the sky would, if somebody was to look up and look for a constellation, is there any bearings like where, if just a person, any walk person that's going to be looking up, where was this at?
This was in the constellation of Hydra.
Okay.
And if you look on your, go into Stellarium or go online and say, where is the constellation Hydra? Hydra. You could see where that is. Okay. And this is for Amanda. You've always wanted me to get into the mythology and the Sky Tour live stream.
I was just thinking. Yeah, go ahead.
I know. Okay. Well, I just wanted to let you know that moving forward, I'm going to actually spend time discussing some of the mythological meanings behind the places we go to in the sky.
Cool.
Oh, yay. Thank you.
And that's because you've asked a couple times, and I've always said, yeah, I'm not interested in that. And I can't tell you that I'm highly interested in that. But you know something? I can't take away that it is very interesting stuff nonetheless. Okay? So we're going to explore that.
Well, I was just thinking, Hydra, is Hydra not the snake where you cut its head off and either another one grows back or possibly two grow back in its place? I don't know.
Is that Medusa?
No. Medusa, when you looked at her, she turned into stone. Yeah. But anyway, with Hydra, I'm just thinking, like, what if this collision was like the head of the snake coming off and it'll be replaced by something, a new head? What do you think is going to occur in, I don't know, like, if the two neutron stars collided, there must be like a specific point, even if everything, either disintegrated or exploded or whatever happened afterwards, there must be a point when they first touched, right? So what do you think would appear? I mean, maybe it's going to be another millions and millions of years, but what do you think would appear there?
Well, actually, we saw the optical counterpart so far. Now, just imagine, these like the things with the consistency and hardness of, say, a billiard ball, like they were saying, orbiting each other. When they collided, then as they were hitting each other, they were shearing away that surface from each other. I don't think that the star would actually be able to maintain its form, all right? Either star. And I think that it probably, if it somehow coalesced and merged into a black hole, it would definitely be a lightweight black hole. But I think more likely there's going to be an optical counterpart, in a couple of years that we'll be able to actually see if it's there. Now, this galaxy is very far away. And Hydra is actually visible where we are at Sky through a live stream. We actually can see Hydra. It's actually down below the constellation of Leo, all right? And it's a fairly extensive constellation going across the sky. It goes underneath Sextans, Crater, and Corvus, which are 3 more constellations to the left. All right. So, and the odd thing is, right now the moon is actually traveling through. It's traveling near Leo. It's traveling through Leo right now. So it actually has a kind of a correlation because the moon is right above Hydra at the moment, which is cool.
There's been a lot of weird lineups lately going through mythological stories.
Mark, going on what Amanda just said, is it possible that the projection of the expulsion of these heavy metal elements could have created celestial bodies?
Well, okay, not yet, as far as I would say, because what happens later on is that these heavy metals are going to be, spewed out into the universe further, and right now they're being formed by these heavy jets of material that are shooting out, and they're shooting out at very high energies, and they're creating immense pressures in the interstellar medium, and they are definitely going to end up being, eventually settling into a new solar nebula at some point, stellar nebula, where they will form the components of planets to form. That'll be probably down the road.
Right.
By a few billion years.
Wow. That's amazing. Amanda, any more?
Oh, lots more.
Go for it. I'm gonna sit
to
back.
Keith from P&K Space Imaging. He just showed up.
What's up, Keith?
Hey, Keith, what's up?
If you haven't already subscribed to his channel, check it out and hit the bell for live notifications.
And for those watching, it's P&K Space Imaging.
That's right. That's right.
P for Paul and ampersand and a K for Keith. Space Imaging, all one word.
If you look in the chat, you can see it right there, and then you can click on his name and subscribe. I did a long time ago.
Me too.
Yeah, me
they
too.
didn't disappoint. They've never disappointed.
Never.
Okay, and this again may have been touched on, but Daryl was curious to know how they could differentiate between black hole mergers and neutron star mergers.
It's just the characteristic of the energy release. They could actually figure out the masses, and the masses tell you what you're looking at, basically. Because if you're looking at something that's between 8 and 10 solar masses, you may be looking at a neutron star. But a pair of them that are like 20 or 30 solar masses, you're probably going to be looking at a black hole for sure. So I mean, there's a way to calculate that, and they did, and that's what they said they did. So I don't know the exact data they were looking at to do that calculation, so I can't speak to exactly what they did.
Okay, and Bill, just to let everyone know, you are going to keep this video up. You're going to upload it, right?
Absolutely.
Okay, wonderful. So anyone who is late coming in, you can go back and watch both of the panels in full. And they're actually in the first panel, they had quite a few videos of what kind of, demonstrations of what happened and blah, blah, blah.
Yes,
so
and
check that out.
And everybody sort of had a different idea. One person showed these rapidly rotating neutron stars just come together. Another person showed them come together and shear each other to pieces, and then a bright explosion. Remember, that's mass converted to energy there. Okay, so when that happens, especially at these relativistic speeds that these things are traveling, there's a lot of mass loss that occurs. So I'm not convinced yet that they would form a black hole, and neither are they actually. So that's why there's discord on what good-natured discord, intellectual discord on whether this actually formed a black hole, or just a bigger neutron star, or obliterated itself. That's all.
Okay, and now these ones all started coming in through the first panel discussion, so I can't tell you exactly what part of the conversation we were listening to when it came in, so just take these as kind of general.
Okay.
Victor, who I think has left the chat now, he asked, or wanted clarification on, so we don't need to check for size and distance, but for a buffer. Was there anyone that was saying...
Don't need to check for size or distance, but a buffer.
Yeah, so now I'm not sure if that was in reference to the neutron stars themselves.
I think it sounds like a reference to the proximity to that event. But I could be wrong.
Okay, because I think he's left chat, so...
Well, distance is important. That's the whole point of upgrading it to get to get to a further distance where they can do observations. So maybe a buffer, a burst, or how they detect it.
There was one part, didn't they say something, and I'm going to mess up the numbers, but didn't they say, like, it took, like, 100 million years, and the movement they saw between them was, like a micro magno inch?
Well, yeah,
and then when it got closer together, it was like the strand of human hair.
He said 30. He said 30 million years just to go from 2 miles to 200 feet.
Right.
And that this existed for 11 billion years. These neutron stars.
Yeah, and they're probably left over from supernovae that occurred when the galaxy or universe was fairly young. And thus they didn't have a lot of other chemical, elements, that is, other stuff in the periodic table within them. Mm-hmm. And of course the neutron stars, that is the stars, but the neutron stars are all neutrons. And that's actually fairly interesting that occurred this way. So, and I'm just reading a comment by Keith. And yes, you're right. Okay. They basically did have Virgo looking in a blind spot. Virgo caught the object, and that is exactly how they were able to narrow down the location. So he's exactly right. Actually, Daryl said it too, yeah.
Yeah, see, and this is what I was going to ask. Like, what if it took so long to move what we consider so little, like, was it just they were both in the right place for gravity to start pulling them together as they swirled? Or, like, could something have knocked them out of each other's orbit? I don't know if I'm phrasing this right, but, like, what's the possibility of this happening where nothing else interfered and made it not happen?
Well, let me just go back here for a second. These two neutron stars that were orbiting each other didn't necessarily form together. Okay. This, because of the time it took for the neutron stars to get to the point they were in, it's very possible that they were circling and orbiting their own galaxy and captured each other. Okay. Maybe because of the events that may, the supernova event might have triggered another nearby supernova event. The neutron stars could have been manufactured that way, and then the result was that now we had two stellar cores near each other, and they eventually captured each other to circle each other. And they, again, the universe has nothing but time on its hands, so there's no reason that couldn't have happened. So, when people think, wow, that means two neutron stars formed at the same location. No, actually, they didn't have to. All right. It could have been that as they were going through the galaxy as stars, they could have actually formed neutron stars independently, and then or as a result of each other's cataclysmic demise, and then that could have been what caused them to actually capture each other, because the supernova probably fairly well cleared the way and could have made the other star that was nearby perhaps go supernova.
It is, though, possible there could be a binary star system, a binary sun that turned into these neutron stars. Is that possible, Mark?
Yeah, it's possible. And they could have been that they were far enough apart so that the first one initiated a supernova and the second one, and they collapsed into neutron stars together. So that's possible.
Any other questions, Amanda?
Yeah. I was just kind of off thinking about possibilities and stuff. Never mind. This is crazy information. And see, I didn't even understand really what we were hearing. Like, I got the basics, but hearing the possibilities as Mark explains it, this is very, very exciting news. I'm really glad that I was here with you guys.
Yeah, I'm glad, because it's really cool stuff.
Yep.
Well, see, like, I didn't, like, yeah, it's cool to find, and it's the first time ever, and that's really cool. But when they were saying, like, things are going to be, like, spread into space that may create, like, new planets and this and that, like, that is, well, like, I mean, you said you think we might see something there in a few years.
Billions.
How long are we talking before? No, like, the point of the whatever happened. Whether they started schlepping off or whether...
okay, I know what you mean.
Is something, if we're going to see something there in
black
a few years...
hole, or is it neutron, or gone completely?
Well, yeah, I mean, the point is, the way we'll see something there will depend entirely on how far away the something is from this planet. Mm-hmm. If it's something nearby, then we will actually be able to see something fairly soon. If it's not, well, then we won't. Right now, this galaxy is just under the sun. So we have to wait until the nighttime, in another season, when the sun isn't in that part of Virgo. And then we'll be able to actually, actually see it at that point. We won't be able to see it, now. We won't be able to look at it now.
They said that a month later, we would have never even caught this.
Right, because look where it is. I mean, it's in the daytime sky now. Mm-hmm. And that's actually problematic, isn't it?
But I mean, I don't know. I'll just stick to the listeners' question.
No. That's okay, because what you're asking is something someone else is probably thinking.
Yep.
It's quite all right.
Well, okay, what they just witnessed.
Yeah.
Is that possibly what happened that created us? Is that kind of what they're suggesting? That this could create a whole another solar system?
That's interesting. Now, I just want to go back a bit to help you here. You had mentioned 130 million years. That's actually the distance of this galaxy. It's 130 million light years from the Earth. Okay? So at 130 million light years from the Earth, we have seen supernovae that occur in galaxies that far away, and they're very bright for a period of time, but then they fade over the course of a few weeks. This faded over the course of a few days, right? So it's a very different event, much more rare. Since there's so many planets out there, there has to be a way that planets are made a lot more commonly than through merging neutron stars. Because if we only had to rely on merging neutron stars, we probably wouldn't see as many planetary systems as we do. And by planetary systems, I mean star systems with planets, So I imagine that it's more likely that supernovae can kick off these events. But understand that when a supernova happens, a supernova scours the area near it and pushes all the material away from the star. And that stuff ends up going. That stuff moves away from the star at very, very high speeds, and then when it hits other stuff in the interstellar medium like dust and other debris, which interstellar medium is full of, it causes these shock fronts, these bow shocks, these areas that compress gas and dust along this front, at supersonic speeds. So, and so that is a process that kicks off star formation. And once that process begins, then the star, when it begins to form, the material falls into this gravitational concentration of matter. Well, it falls in with some motion, and that motion translates into in the end, a planar accretion disk, right? Because accretion disks are a natural consequence of this formation process. What's an accretion disk? It's a disk of material that forms around a forming star, or even a planet. It may become a ring or something. But around the star, it's a disk of material that can go out for tens of millions of miles.
So it kind of flattens out, right?
It does flatten out, yeah. And that's because of the gravitational interaction. It tends to want to normalize itself. And it really depends on the rotation direction of the material, all right? That's why all the planets that we have in our solar system, they move through our former accretion disk, okay? And that's important. See, I mean, they don't just form at odd angles to it generally. They form kind of within the accretion disk, and they circle the star in that direction. So that said, when we see all that, and we look at how this forms, the shock of a supernova occurring somewhere could, in fact, have kicked off star formation in a little nebula, 2/3 of the way out in our galaxy, and caused our sun to form, which then caused all of our planets to form from the material that was transported here over billions of years of supernovae and compressed via perhaps a nearby supernova that we'll never, ever know about.
Mark.
So it's very cool.
Mark, when you have these events happening within, say, a galaxy, and it's coming from all these different directions, does that help it merge together, or is it still traveling in a spiral formation and it just spirals together? You know what I mean? Say we have it in one section where you're having a supernovae, or maybe across the other side there's another one going on, but they're coming out from they're expanding from different directions, and it's coming together to form these bodies?
Well, it's possible. I mean, I can't say it's not, but one thing I did want to point out is the galaxy in which this occurred is a galaxy called an elliptical galaxy. It's not a spiral galaxy like our Milky Way, like Andromeda, like the Fireworks galaxy, like the Sombrero is sort of a tight spiral. Okay, it's not that at all. It's more like basically a spherical collection of stars. And there's some physics work that shows that elliptical galaxies, which are, not uncommon at all. Okay, Andromeda has 2 of them. Actually, has satellite galaxies around it. The Andromeda galaxy has them. These elliptical galaxies are actually very much more, older than a spiral galaxy, perhaps. In fact, that might be the end result of collisions between spiral galaxies, for all we know. And they have many stars. They're massive, massive collections of stars. We're looking at the universe from within a spiral galaxy. If we were within an elliptical galaxy, like only 1/3 of the way out from the center, we might have stars almost everywhere we look. And then Olber's paradox might actually be true. If you remember Olber's paradox, it says that, if the universe has so many stars in it, then how come, everywhere we look, we don't see a star? Well, that's because we're living in an architecture. We're not living in a homogeneous layout. We're living within an architectural spiral arm of a barred spiral galaxy, which is our Milky Way. And so that's interesting because when we talk about this stuff, when we talk about the looking out from within our galaxy, if we look to the galactic north, we're going to look through relatively few stars. When we look to the galactic east or west, we're looking through the spiral arms.
Right.
Okay. Right. So it's denser. we look toward Sagittarius, we're looking toward the center of our galaxy where it gets thicker and thicker stars. All right. So there's a that's really interesting, to me. And so I think that if we look at the fact that this is an elliptical galaxy, they're going to have stars that are orbiting it in a similar way, but not quite like a spiral galaxy has stars orbiting it. So events might tend to be a little bit more, I don't know, I want to say randomized, or they might occur in a way that's a little less than regular. You probably, each star in an elliptical is orbiting the galaxy, but it might be orbiting the galaxy in a variety of ways. Kind of like the old depiction of a spherical atom, where we had electrons going every which way around the outside. Maybe they do that in the elliptical. Okay, if they did it in a regular way, we'd see that. We would see the result. We'd see the result of trailed, supernovae debris that would leave dust lanes and dark lanes in these galaxies, which we don't see. So it's really interesting. And Keith, in the chat, he just mentioned something about Pauli exclusion principle. The Pauli exclusion principle basically says, and I want to talk about this because it does relate to neutron stars and to white dwarfs. Okay, it actually directly relates to why they can stay structurally sound like they do. The Pauli exclusion principle relates to electrons, the lowly little electron, and it relates to them because it says that electrons that are in different quantum states, okay, can't all be in the same quantum state. They each of the electrons, okay, within a system, within an atom, have to be in different states. All right. So that means that if you have 1 million hydrogen atoms, then the electrons in those hydrogen atoms have to be in different quantum states. All right, within each atom. Okay, but within the system as a whole, they act like they're in all these separate states. And it's not intuitive, and I'm sorry that it's this way, but you kind of have to take the word for it. What that means is that when you have a system like this of a white dwarf, which is a very compact material, the material on the surface is labeled degenerate material. The electrons are freely moving. These electrons can't be in different quantum states. They have to be in different quantum states. It can't all be in the same state. That's actually that gives rise to something called the electron degeneracy pressure. It's actually the pressure that holds the star up, and it's what keeps the star from collapsing further. All right. So that degeneracy is sort of key in physics, astrophysics, quantum mechanics to discuss when you talk about why a neutron star looks like it does, acts like it does, why a white dwarf acts like it does what it does. Because there's not just electron degeneracy pressure, there's proton degeneracy, there's neutron degeneracy. And they all come into play with these different types of stars. The thing about this is when these two merging neutron stars collided, okay, you bet your butt that degeneracy pressure from those neutrons at the surface was disrupted in a huge way. So I can't imagine, because I've not seen it before. I can't imagine that it came back and it actually, the neutron stars collided and merged in a very, easy way, kind of like water droplets in zero gravity, like in the space station. Mm-hmm. You bring them near each other and they go bloop and they collide.
Yeah, they said it was very violent. They did say that. It was a violent merge. So
right, and violence usually means impulse energy, and that is energy that's transmitted to the system from moving material that's moving at a high speed, and that moving material has the consistency of like a billiard ball, basically. Like I keep using that analogy because they did, but that is something that's really, really interesting to consider. And so that had something to do with this. I know that the energy released was just a massive amount of energy. Mm-hmm. And of course, they do too. But I know that the fact is that when that stuff released all that energy, a lot of the mass that went into this was released as energy and converted to energy. That happening tells me that, I don't know. I mean, maybe I don't understand the full numbers yet, But I would not guess that these turned into a black hole. I know that the jury is still out on that. Again, I'm just making my suggestion is that these probably obliterated themselves.
Mark,
but that's just me. Yeah.
Just to give a perspective on the density, the volume, the compression of a neutron star, because they said they gave an illustration of a neutron star, say over San Francisco Bay, 22 miles wide.
Yes.
And like you said, you have two of these highly compacted, dense objects colliding. So you would figure logically that this coming together, this merge, this collision would, like you said, produce all this high energy going off.
Yeah, I mean, it's a very energetic collision. It's a very energetic process. So, again, the galaxy that it happened in is 130 million light years away, and we saw it. We saw it brighter than any object in the field, in that galaxy. And there's a reason. The reason is because that energy release was so incredibly large. I believe it's actually an obliterative event, an event that actually
scattered.
Yes. Yeah. I just thought that to me is what it was all about.
Amanda?
Well,
Yeah. Okay. This one came back again during the panel, so I'm not exactly sure what he was listening to when he made this comment, but I think Daryl wanted clarification on lesser amplitude due to mass, but longer duration. Is that what they were suggesting during the merger? Or? Sorry, guys.
Just like name that tune. We hear just a fraction of the song, and you got to recreate what the song was in your head.
It would have been earlier on.
So read that again.
Okay, well, lesser amplitude due to mass, but longer duration.
That's not even a question, but it's just a statement, right?
Yes, that's why I said I think he wants clarification. I'm not sure what he was listening to, but it looked like he was looking for clarification. I think it was before you were in chat anyway.
You said lesser amplitude?
Due to mass.
Due to mass, but longer
duration. So that's what I'm thinking.
The only thing I can think
when
of
they were coming together.
I think maybe what he's talking about is, the duration wasn't long. Actually, the duration of the impact was very fast.
Yep, seconds.
Yeah. I don't know, but I do that. It does remind me to say something else here. When they talk about the actual mechanics of what happens when those neutron stars merge or collide, I should say, or maybe even shear themselves to pieces, as they say. Neutron stars have a very powerful gravitational field, or else they wouldn't be neutron stars. Their degenerate matter on their surface is held together, very, very compact. Hundreds of millions, if not billion tons per teaspoonful.
There you go.
Okay,
that's why I mentioned density. Yep.
Yeah, and if that's the case, when they shear together, disrupting that organization of that star, which isn't even really technically a star. I mean, it's not doing fusion. Okay, it's actually just a hot leftover core from a previous cataclysmic event. So that said, when that happens, and it does start to shear off stuff, start to do that shearing process, that whole process is affected by the tidal forces of the gravity of one star affecting the other star. And once the break starts to happen, then the material that's been loosened and freed from the surface of one star is going to go streaming violently toward the other, and vice versa. And in that process, where they meet in the middle, if they meet, they might not meet. They might be streaming in two different paths, and not just go straight through. Where that happens, there's going to be a tremendous release of energy, and in this case, because the duration was so short, that tells me that this happened very quickly, right? And obviously, and Daryl says in chat, the black hole mergers, happen in an instant. Not I guess if you think of them as two singularities, which are infinitely small points, and yes, that's instantaneous. But you got to remember there's an event horizon that's farther out from a black hole, and there are tidal forces, magnetic forces that are also out in the event horizon. We do see radiation coming from locations of black holes. That's how we know they're there, right? And that's all happening with these really strange interactions on the surface near the event horizon of these black holes. That is the point where light can't escape beyond which the light can't escape. And so clearly, when these neutron stars were merging or combining, the material streaming off in that last instant was going through their very center of mass, to the center of their mass, and heading to the other star. But it was happening mutually. Okay, the neutron star one was probably breaking up as the other was breaking up, and then they started bleeding bleeding debris through that central location. And if it was a small enough location, that debris would collide, and that collision was probably hugely energetic. Is probably the reason that it took so long for them to die down, several hours. I mean, if it happened fairly quickly, then it could have just been a flash. It was like gets bright, kind of like an iridium flasher. Mm-hmm. Gets really, really bright in the sky, then it dims out after a few seconds. Mm-hmm. If it was that fast, it would have happened that way. But the fact that it wasn't shows that maybe at that point where the matter was colliding with the other matter, streaming in, and that mutual streaming from each star to the other, where it was colliding might have been the energetic event we were seeing. Andy Morrow, you're going to HE double toothpicks for that comment. It is funny though. It is funny, Andy. Just keep it on. Keep it serious now. Anyway, he's funny. So, but that said, I think that collision will definitely be studied for years to come. And maybe they'll change theories. Maybe they'll change things. I think they're going to discover that it was obliterated. That's just me.
Mark, do you think they need other observations of a collision between neutron stars in reference to this one, and see the effects of that, like you just described, that it may have been rapid, or maybe there's a slow process where the light is seen dimming, that they can, in other words, they need more data to relate to this event to give them more information.
Well, they certainly do. And I know that they talked about it at the press conference. They talked about doing a lot more work like this. They also talked about, other instruments coming online. Yep. They also talked about amateurs. Yep. And they said Sky Tour Livestream is going to play a vital role in pursuing this someday.
And P&K. And P&K space imaging.
They didn't say that, but that is something that, would be very important, is to get everybody involved. Yeah, in this age of crowdsourcing, not everybody, though, has access to a telescope of sufficient size and capability to do this. My telescope here probably is at the lower end and probably couldn't explore that galaxy in the same way that somebody else better equipped could. But I could provide a data point as long as I had a calibrated instrument to measure brightness and or acquire data in different spectral regions for them. And that's the kind of thing,
But the thing but see, here's the con on this. Do you see LIGO, Virgo, all these other observatories, and they discussed this too, providing the public with access? Like you were mentioning it earlier, looking into the app for the work that you're doing with Doug, to put this out for the public so they can get this alert almost instantaneously, so they can start pointing. Do you think that is going to happen realistically? You see that happening? I hope so.
Well, there's no reason it can't happen now. I think the only reason it hasn't happened is because the science community has actually kind of been slow to embrace, cloud processes. There are some scientific organizations that actually do look forward to embracing this type of opportunity. These guys, ESO, probably would. but they're also made up of a lot of older people who don't have the same understanding. They're geniuses with astrophysics, but they don't know Facebook worth a darn.
Right.
For instance, and that's Facebook isn't worth much to them anyway. But I'm just saying,
a media platform, a social global media platform.
Yeah, they need a global social media platform. And Bill, you're just the guy to get them to do it. So go ahead, let us know when you got it done. We'll be waiting here in chat.
We'll do this a couple of more minutes because I have to actually hand over the radio station to the boss.
Okay.
And we've been streaming a little bit over 4 hours now, I think. Amanda, is there any more questions?
Yeah, we have lots more questions, so we'll try to get through them quickly.
Okay.
Okay. Victor asks, how much mass in a certain area of an object, like a planet or a star, would we have to place on it to shift from its axis or place in space? And would it domino effect like bowling pins?
That's an interesting question. It's a little off the wall, but I understand where he's going with that. Well, we can take a look at our moon to actually go for some of the answers to this question. Our moon is not, our moon is oblong. Our moon actually is off center, so to speak. The center of mass of our moon is not in the center of the moon. It had to do with when the Earth and the moon formed. The moon was molten on the near side, primarily because the Earth was molten on most of its surface. And when stuff was sent up, into the exosphere of the moon, that is the area around the moon, it was it tended to go to the far side, the side we don't see, and it settled there. And that made the crust on that side very thick. So, as a matter of course, the moon became lopsided, actually, and so the moon doesn't have a center of gravity that's in the center of the planet. The Earth does, but the center of gravity of the Earth could be changed by tectonic activity. When we had Pangea years ago, millions of years ago, Pangea and earlier Rodinia, when we had that supercontinent on the Earth, that probably made the Earth a little bit lopsided. But no, that's not why the Earth is leaning on its axis. That's for a lot of other reasons, probably due in part to the tidal activities of the moon working on the Earth, plus the origination of the moon itself from the initial collision. That could have been part of it. So I don't know the answer to how much mass would be required, but you can see how it has happened in the past. When we look at the moon, we look at the Earth. There are subtle changes that occur as well. What caused Uranus to be lying literally 90 degrees, almost 89 degrees, almost on its side? So what caused that? What caused Pluto to actually not be orbiting the sun in the plane of the ecliptic? That is where all the other planets orbit in that disk. Why is Pluto several degrees above the ecliptic on one side and below on the other? Because it's obviously crossing through the solar system plane every so often as it orbits the sun. What caused that? Something had to happen to cause that. It's probably all due to the dance we do with gravity in our solar system. Because of the dance of gravity between Earth and Moon, we have an Earth that's 28 or so degrees on its axis away from the center. So, and because of that, because of gravity, we actually have a Pluto, a dwarf planet that's actually 17 degrees or so above the ecliptic of our solar system. So I think that, or not 17. I think that it's important to understand that gravity plays a huge role, and of course the distribution of mass can change the gravity of a local planet. Now we say, well, wait a minute, how can that be? Because what we see is that we always say that the gravity acts as the center of mass, at the center of mass of an object. Well, it does. But if the center of mass of an object shifts a little because you have more mass on one side of the object, like when we had Rodinia and Pangea on our planet and not the distributed continents we have now, well, then that will change things. Okay? And like the moon, we see it now. The moon does have a center of mass that's off center. And it is, it does have effects like that. In effect, if you want to exaggerate it a little, the moon is kind of shaped like a football, right? With the 2 points, one pointing at Earth, one pointing away from the Earth. And so that kind of helps the moon stabilize in its orbit. And it could have gone either way. We could have had the far side facing us, and we could have had the near side away. But it just happened to be this way. And then the further effects that occurred were that the Maria that we see on this side were the result of the crust on this side of the moon being thinner from that process I mentioned before, where material that would come off the surface of the moon would tend to go into the exosphere around the moon and tend to be pushed to the far side by the radiative infrared energy in part from the still molten Earth at the time, or still partially molten Earth. So that would tend to push stuff to the other side of the moon, where that side of the crust became thicker, and further made the moon more oblate. And that's then once it was there, the moon locked into position. It'd probably be quite a bit of energy to shift the moon around the other way. And maybe someday we could figure it out, but right now there's nothing we can do. And not that we want to. We don't want to mess with our tides, but it really is. It's the dance of gravity that caused all this.
By the way, I can't resist Mark and Amanda, but I just got to do this.
Oh my God.
I got to do it. I just got to say it. And the impact that happened millions of years ago here on Earth did not make it flat.
Oh, Bill, you're so uneducated. Of course the Earth is flat.
I had to do it, Mark and Amanda. I just had to do it. All right, Amanda, go.
I did not see that one coming, actually. Nice.
Yeah, I didn't either. I actually thought he was going to say something else, but that's good.
Okay, Charles Smar says, neutronium hits neutronium. Do we look for a cork bubble?
What's a cork bubble?
I don't know. I was hoping you'd tell us.
Are we talking? Did he say quark or cork?
Q-U-A-R-K.
Oh, okay. I think he said cork. C-O-R-K.
Oh, no.
Yeah. Well, okay. One of the issues with I think he's talking about. Is he talking about neutrinos? Probably.
Maybe.
One of the problems with neutrinos is they're very, very hard to detect. Only large, deep underground, giant tanks of ultra clear, perfect water can detect them with any reasonable accuracy. So I don't know if he's talking about that. But neutronium versus neutronium, is there even there's no element named neutronium, right? So I don't know what he's talking about with neutronium. I guess maybe
I don't know. That word threw me too, but I figured.
Well, it's a hypothetical, obviously. Okay, and so basically, I guess it's basically like a chunk of a neutron star. You might say is neutronium. So I don't know whether neutronium, if it even exists, is something that could actually be, something we could look for. I don't know if we see any effects of neutronium hitting neutronium. So I guess what I'm saying is I don't know the answer.
Could it be the matter in neutron stars?
No, that's what I just said. Yeah. Yes, the neutronium is theorized to be the matter of neutron stars, which is all pure neutrons. But we don't even know what that looks like or what that's like. And for that to be in existence, we imagine it, like a cube of it sitting on our desk. If we had a cube of it sitting on our desk, an inch by an inch by an inch, it would probably burrow right to the center of the Earth and go through the desk and go right through the floor, and because in a way.
Oh, I just got to add the boss really quick and just tell him what's going on.
All right.
Okay.
What's up, Race? You're on the live Skywatch with Mark, Amanda, and myself. We're just
What's
about.
What's up, brother?
Hello, man. How's it going, everybody?
Hi, Race.
Race, I'm doing good.
Dantonio.
And that's why Race has a radio station.
Yes.
That voice is magical, man. I've always told you that. KGRA, the blowtorch of ufology and the paranormal, let me tell you.
Well, what's going on in the news? Did they make the announcement? How's it going?
Good. Yeah, the announcement was made. They actually discovered, they made this discovery before that they saw merging neutron stars that actually released these gravitational waves, and then they actually saw the big news. And I know it doesn't make a lot of sense to a lot of people, but the big news is that merger resulted in light that could be seen from this galaxy 130 million light years away. And you could actually see the light. It was blue when it first came out, and then it faded faded to red as it got cooler over a period of a few days or a few hours. I can't remember. Let's say a couple of days, right? So it was like just an amazing event, and it starts a whole new era of astronomy called gravitational wave astronomy, and that brings us one step closer to understanding what gravity is, Race.
Well, it's about time.
It was
you don't think, huh?
It was a celestial merge, just like another celestial merge that may happen. KGRA TV and Sky 2 live stream.
Sky Tour live stream. That's going to happen.
If that's
it's going to happen. There's no two ways about that. It's just getting all this stuff together, dude, between 8 of us.
I know.
That's like 5 people trying to move 150 person circus. You know what I mean?
Yeah.
And we won't forget about P&K Space Imaging too, the moon guys.
Oh yeah, absolutely, absolutely. Speaking of, I called you to get the station off your hands. You've been hauling the mail for 2 weeks by yourself, and I know you're ready to get rid of this thing. So
we're gonna do that. We're gonna Race. Are you gonna be around in like 10 minutes? Because I'll wrap this up with a few more questions, and then I'll be in contact with you.
I'll finish my lunch, and you can just give me a call then.
All righty, Race. And thank you for coming on with us.
Thanks, y'all.
Later.
Hey, Race.
Take
See you
care.
later.
Did I tell you I had to give the station soon? I said it. He's right, too. I had it for 2 weeks. So,
yeah, and he's right. You want to probably get rid of this thing. He said, well, it's like, too much of any good thing,
Yeah, well, Amanda, we have about 10 minutes.
We still have a few more questions.
Yes,
Mark?
we have time for a couple more.
Okay. Okay. Ian asks, he wonders how, when or how long ago this actually occurred. Now, if it was 130 million light years away, does that mean it happened 130 million years away?
Ding, 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 ding. You got the answer.
Yep.
That's very good.
You got it.
It happened 130 million years ago. Yeah. And we saw it only now because the light train from the event just got here. So we're seeing that whole galaxy, that whole elliptical galaxy, as it was 130 million years ago.
That's amazing.
Yeah. Further, that galaxy is probably in a totally, different position in the sky. I don't mean really, really far away, like over here and then over there, way over there, but it's shifted in the sky somewhat too, because it's also moving through space. We're moving through space. Our view moves through space. So, I'm sure that even now that galaxy isn't exactly where we think it is. So there's a lot, that whole thing, when you think about this, it's all relative. And the universe is a time machine.
Next question, Amanda.
So, okay.
Yeah, because we only have. I don't mean to be abrupt, but I definitely got to get running soon to give him the station. So we'll try to get as many questions as we can in the next few minutes.
Just a few more, yeah. Charles wants to know: would tidal forces stop the spin of a pair of neutron stars?
Actually, sort of. I don't know how to answer that in a way that's clear. Let me say it this way. Not per se. And let me explain why. When we look at the tidal forces didn't really start to impact each of these stars in a destructive way until the stars were a few hundred feet apart. Okay, because they have such massive gravities that they are very, very well structured. Okay, very solid material. So the tidal forces started to tear them apart as they began to almost collide, in that time frame. So that's when the tidal forces actually began to start pulling them apart. But the tidal forces wouldn't tend to do anything but destroy, not recreate further objects. It wouldn't put them back together typically. It depends, though, on how fast the collision occurred. Based on the fact that it took a couple of days or so for this stuff to dim away, that says that this collision probably took enough time so that the stars could actually crack apart and show us energetic events where the material is crossing their barycenter between them, and then light up the sky that we could see it. But I don't know if that means that they actually did more than just break apart. So I don't know the answer to his question directly, but I do know that this is an event that has really kind of thrown us all for a loop. Never seen this before.
Okay, Marco wants to know, is there a black hole at the center of every galaxy?
That's the current theory.
That's the current theory. Okay.
The prevailing theory is that there's a large super black hole at the core of the galaxies. Yep.
Okay. Our good friend Lorraine, she says, earlier in the video, they mentioned the use of titanium gold in a project. What is that? Is that a condensed form of hard gold?
I don't know the answer to that question. I'm not a materials engineer guy, but it's probably it's probably something that relates to the actual instrument material that they're going to make the material instrument out of.
Okay.
I don't know the answer.
Okay, no problem. 2 questions left. Dusty Witch. I'm very curious why there was a chromatic shift in the light from blue to red in the event. Why would light be moving towards us and then away as the event decayed away within a few hours?
Actually, that's a misinterpretation, but I'm glad you asked that, Dusty, because you're not the only one that probably had that thought. It also, the color of the light also, if you've watched our Sky Tour live stream, you've noticed that I've talked about the OBAF-GKM stellar classification schemum, all right? And stars that are very, very blue are also very highly energetic. It doesn't mean they're coming toward us. There is blue shift and red shift, yes, absolutely. However, in this case, the blue means it was a highly energetic light, okay, very high temperature, very highly energetic. But then as the temperature started to reduce, as the material and the reaction waned, it heads more toward the red. So it goes from being basically blue hot to white hot to yellow hot to red hot. And that's basically what that is. Red hot versus blue hot, opposite ends of the spectrum. So that has to do with the energy, not the move. There's not movement of the object. But I'm glad you asked that, because that was actually a very important thing to clear up. Mm-hmm.
Yeah, there was some conversation about it in the chat, so I just wanted to hear what you had to say about it.
Yeah.
Okay, and the last question is from DJ J-Town. If it isn't visible, I think that's what someone said, but has an infrared signature, has it collapsed into a black hole? If not, what has happened to it? And that's kind of where we are, right?
Okay, well, I think that infrared, is an end result for some things. That's true, but a black hole won't necessarily emanate infrared radiation. Certainly, it doesn't irradiate any radiation at all. But at the event horizon, if there is dusty material being drawn into this black hole, that material is going to be heated up very much so, and we'd see an infrared signature from that. Okay, usually black holes emit radiation like gamma rays and things like this, so we would actually see a different form of radiation coming. Gamma rays are very high energy, and infrared energy is actually very low end, longer wavelength energy at the other end of the spectrum. So we would see one of the two, but not for the same reasons.
Well, I have to say this was fascinating, the last few hours. And Mark, as always, an informative, educational experience, not just for Amanda and myself, but I'm sure for everyone that was watching, explaining pretty much what was discussed during this press conference.
Yeah, I'm just a talking head like you see on these shows. And you go, who's that guy? What does he know? You know?
And this is why, folks, you've got to go to Sky 2 Livestream on YouTube to experience this for yourself on Mark's channel. When like he said, to put the video and the audio together, and it just makes for a great experience on his channel. And also, we can not to forget, also the great job, the great work of Paul and Keith at P&K Space Imaging. That's another highly recommended great YouTube site for what they do there, observations of the moon and other planetary bodies. So, and I want to thank everybody that's been watching, and of course all our friends in the chat room, and Mark and Amanda, you guys are amazing.
Hey man, thank you.
And
thank you so much for inviting me on. I was gonna loiter anyway and try to grab questions as they came up, but wow, thank you for inviting me on air with you guys. I enjoyed it, but even the pictures they were showing, I was getting lost. So thank you so much, Mark, for answering these in detail and really helping us understand, because now that I understand some of what's going on and some of the possibilities, I mean, it's more exciting than watching both of the panels. Now that I understand, it's crazy, and this is quite an experience. A first in the world.
Yeah,
we're all here to share it. That's awesome.
Yeah, and like I said, you just don't want to put astronomers and astrophysicists in charge of the entertainment, because that's what happens.
Yeah, I thought they were going to start throwing things at each other on the panel.
Well, it's just that they basically, they're speaking so excited about something that hardly anyone in that press group could understand. Mm-hmm, mm-hmm. And you didn't have someone there who could translate it. A couple of the guys were a little bit more down to earth, and a couple of them, one of the guys was actually one of the women that was speaking was actually I understood her approach. She was trying to help out, but she was being misguided, I think, and kind of simplifying it too far by saying, and then this star went on vacation.
Oh yeah.
Yeah, that was like a little over the top, because she was trying to. All she was trying to say was the star went around the galaxy a number of times.
Right.
But I think she was intimidated by her own intellect, and she thought she had to oversimplify, and she didn't know when to stop. I love her to death. She's a great person.
You know what? It was funny when the last reporter, the guy that had the press badge, it said press on him, and he asked that last question. So why is it so important that LIGO and Virgo was essential to all of you? Why didn't you guys get this in the past with your equipment? Meaning all the electro. Yeah, and you saw how
you gotta laugh.
But did you see how they all came up? They all wanted to talk at the same time, because
yeah,
that was classic, because they all were ready to say, well, whoa, hold on. It was funny. It was classic. Yeah. It was great. It was really a well done press conference. And now there was another one that we did not air here, and I'm gonna look at what they had to say.
That was the ESO.
Yeah,
that was the ESO announcement.
Yes,
they did their own.
Yep.
Was it on the same thing?
Yes.
Yeah, it's on the same topic. Yeah.
Okay.
The European Southern Observatory.
Correct.
And I think it was in Germany, Mark.
Yeah, I believe so. That one was based in Germany. The ESO is not in Germany itself, but the press conference. The conference was.
Well, Mark and again, Amanda and everybody watching and everybody in chat, again, thanks to everybody. And hopefully we're going to be doing this again a lot more frequent, because from LIGO is going to be down for a bit. I think they said for a year.
Yeah, an update. They got to do an update.
Yeah, but I'm sure we're going to hear a lot more of this in the future and other celestial events. And when we do, we'll do it again. And don't forget, Mark, are you planning? I think it might clear up tonight. You planning to do Sky 2 live stream?
If we have a clear night, I will be Sky touring, because of the fact that it's just in my blood. It was clear last night for a little while, and I was walking out to the observatory, and I realized, I have a bad feeling about this. I'm not going to open, and I didn't, and it was a good thing, because it ended up being cloudy.
Yeah.
Yeah.
And also,
but yes, if it's clear tonight, we're going to have a Sky 2 live stream. If you subscribe and hit that bell, just like you do with Paul and Keith, because those guys are great. If any of us are streaming, or Bill even, if any of us are streaming, you're going to get a nice notification, so you'll know.
Yep. And
happy to have you.
And just like Mark mentioned, P&K Space Imaging. The telescope is based in Miami. That's where Paul is, and Keith does all the technical work. And that
but he's also going to do some streaming too at some point.
Yeah, he is. Yeah.
Yeah, because he's going to get a telescope if he hasn't already for his location. And a little secret plan is in the works. We might be able to actually do some streaming from other observatories already in place down in his area with very large instruments. So this could actually be a very good thing.
Yep.
But we'll see what happens.
And I got to keep an eye on I got to put a camera in front of my house so I don't make sure that Keith comes with his pickup truck and takes my telescope out in front of my yard.
Well, he won't take your telescope out, okay, because he'll probably have access to one 5 times the size of yours.
Exactly. I don't have to worry about that no more.
but yeah, so you won't have to worry about that. I think that'd be pretty cool.
Yeah,
well, let's hope that happens, guys. And as always, it was a pleasure to be with you guys.
Yes.
I really enjoyed this press conference. I thought it was wonderfully done, and I'll tell you, man, I'm all for it.
I agree. I think a lot of people are reaching the same sentiment that you are. So till the next time, everybody, have a great day, great evening, great morning, wherever you may be. And for those in Ireland, please be safe, in the UK. And those out west with the fires and everywhere else you may be facing some type of calamity, we wish you well, thoughts and prayers. So till the next time, have a great day, everybody, and we'll do it again soon. So take care.
Appreciate that. Thank you. I'm Brian Green, co-founder with Tracy, and I also want to welcome you to Day 4 of the 2016 World Science Festival. The program tonight on gravitational waves. It's a timely program. I trust you all heard the announcement on February 11th, or you read about it. The first direct detection of gravitational waves. Amazing, amazing discovery. And we have here tonight a group of the very individuals who made this discovery possible. I'm going to bring them out in just a little bit, but just a few words at the outset. You know, this discovery, just to put it in context, it's the kind of achievement that happens maybe a few times a century in fundamental science. I mean, we were thrilled some years ago for the discovery of the Higgs boson. Something that was searched for a very long period of time and finally was definitively discovered at CERN. Great discovery. This ranks on par with that kind of experimental observational achievement. And the other side of the story that will come out in the conversation here tonight is that whereas for the Higgs boson, just about everybody was convinced that the experiments would succeed. I mean, most people who were following closely the search for the Higgs boson were saying, well, if it's not found, that's the craziness. I mean, this has got to work out. The theory says it. All of the circumstantial evidence suggests that the particle is out there, and indeed it was found. Now, with gravitational waves, as we'll see, there was never really any doubt after, I don't know, call it 1950, 1960, that these ripples in the fabric of space were a real feature of Einstein's general theory of relativity. But there definitely was controversy as to whether we would ever have the capacity to catch one of these waves. And we'll hear about why in just a moment. But what this means is it takes a certain kind of internal fortitude. It takes a certain kind of vision. It takes a certain kind of stubbornness. It takes a certain kind of independence of spirit to devote your life to this kind of project. And our hats are off to the individuals, they now number roughly 1,000, who made this discovery possible. Okay, a little bit of background before I bring the panelists on stage just to set the stage scientifically, right? So we're all more or less familiar by this stage of the game that Albert Einstein gave us.
Okay. I kind of like fell asleep, and I'm going to cut the stream because I'm exhausted. So I want to thank everybody for being here, Amanda and everybody. So we'll do it again soon. I need to get the camera in and get some rest. So thank you, everybody, for being on. And we'll do it again tomorrow, maybe. So till then, have a good night, everybody. I'm out of here.